have enough information yet about what they're really going to be doing for problems when it comes to this. And we know it's only worth about 10% of the whole test. So my my desire to go too in depth to this is not very high. I just kind of want to breeze through it a little bit, give us a couple of practices, and show us some of the most likely examples we're to see. So I want to begin by first giving you a little bit of an understanding on how you're supposed to use these and in what circumstance. The first one is to talk to you about how Pascal's principle and Bernoulli's principle work together. So I'm first going to talk about closed systems. It's a closed system, so a pipe that has some fluid passing through it. It could be a water pipe in your house. It could be just some generic pipe with some random fluid. But if we want to make this at all realistic, you guys have pipes in your house. They have reducers and expanders that change the cross-sectional diameter of the pipe. It usually doesn't do it in a smooth way like this. Usually it's fairly abrupt. But for this, we want to talk about smooth exchanges so that we don't have what's called turbulence in our fluid, places where the fluid will back up and cause vortexes. So we're going to talk about smooth transitions always because it's simpler, but that's probably not how the real world would work, because if you've ever gone to, say, Lowe's and gone to the section that sells like PVC pipe, you'll find PVC converters that go from one size to another. They don't do it smoothly. They just change the size. And so the result is still the same, but at the point of the junction, you might get extra pressure as that water is hitting the junction. So for us, we're not going to talk about that. We're going to talk about just these smooth transitions. But we are talking about a closed system, meaning that it's not exposed to the atmosphere. In these kinds of closed systems, there are two principles at play. But the one that overrides all of them is that if a fluid is flowing through the system, so we have some fluid flowing through the system, the volume flow rate stays constant. That's like a priority. When I say what thing is the most important, what thing are we sure is going to happen every single time, that's one of them. The volume flow rate in a closed system stays the same. Even though Bernoulli's principle is kind of like conservation of energy, this isn't like a marble rolling inside this pipe, because inside the pipe there's always more water pushing on the water ahead, and there's always water behind pushing on that water. Right? The water is all in the pipe and it can't be compressed, so as the water flows, it has to go through in such a way that the volume per second, the gallons per second, the cubic meters per second stays the same all the time. That's Pascal's principle, meaning this always is first. Because we know that this has to stay the same all the time, we know that if we have the cross-sectional area of the pipe here, A1, and the cross-sectional area of the pipe there, A2, we have an understanding that in this system, the water's slowing down as it goes from 1 to 2. It has to be. The cross-sectional area is increasing, so the velocity has to get smaller. So the velocity of the water here, which is V1, is going to be bigger than the velocity of water here, V2, period. Because Pascal's principle takes precedence. However, there's Bernoulli's principle. And just to make sure you remember, Bernoulli's principle has 3 parts. And I'm going to write it different than yesterday, not to confuse you, but I looked at the equation sheet and I used H here on the equation sheet. If you wrote this down yesterday, you can probably verify that. But your equation sheet uses Y. It means the same thing. Y is a vertical displacement. But I want to be consistent with your equation sheet. So I'm going to switch to Y. But everything else should be the same. This is the first part of Bernoulli's principle. It has 3 parts. Let's just remember what they are. There's pressure. And this would be known as the internal pressure of the fluid. this is kind of like the force on the fluid that's pushing it through the pipe. So the pressure is changing as this thing moves through the pipe, but this is the internal pressure of the fluid. This would also be how hard the fluid is pushing on its container. So this force, this pressure is internal, but it's in all directions inside through the fluid. And again, we're talking about a fluid that is flowing through a system. This part isn't potential energy, but is like potential energy. Because it's about pressure and not force. That makes it like potential energy. It serves the same premise as potential energy. That number gets bigger as the water gets higher and higher into the air. So if you have a pipe that's going up to the second floor, this number is going to be increasing. The last one is like kinetic energy. It's not an energy, but it's like it. It serves the same purpose. Again, all of these actually work out to be pressures, but this one, the kinetic energy portion of it, that contribution to Bernoulli's principle increases when the velocity of the fluid increases. But let's also remember what the other parts stand for. This we know is pressure. This and this both represent density. This is the density of your fluid, which shouldn't change if it's a non-compressible fluid. But if it's a gas, it'll change. But we're talking about non-compressible fluids when we talk about flow rate through the pipe. And obviously, we have this, which is the height. Right, these are all the parts of Bernoulli's principle. This has to stay constant. So if you compare any two places in your closed system, place 1 and place 2, these things have to be the same. Now the reason that's important for us, I'm going to go ahead and take all these off here so I can clean this up. So let's go back to our example over here. Maybe. When we look at Bernoulli's principle and we look at Pascal's principle handles the part about the velocity. So in this example, the example we're looking at right now, we know the velocity here is less than the velocity here. So the kinetic energy part is becoming a smaller number. But also in this example, the height of the pipe is changing. If this represents y1, well, y2 is greater than y1. So when we compare Bernoulli's principle, we know that this term is going to be going down, while this term is going to be going up. Whatever difference occurs there, the pressure of the fluid will change to accommodate and make sure that these are the same. So the pressure of your fluid is always changing as it flows through a pipe in order to accommodate those two values. That's why they always talk about the fact that water pressure tends to be less in upper floors of a building. Because although you can keep the flow rate the same, but you might have less water pressure even at the same flow rate because the water is so much higher if you get to the 3rd or 4th or 5th floor of a building. Now, I'm saying all this to you because this is how Bernoulli's principle works. In practice, we're not going to have problems like this because the level of complication is pretty high, and you can kind of see that, right? All these different things to keep track of. And it's not that it's terrible, but you guys have generally had trouble if we had more than 1 or 2 kinds of energy in a single problem. To throw in pressure at the same time is going to make this tough. But this is what Bernoulli's principle and Pascal's principle is actually about. But again, this is for closed systems. So this is where you turn on a spigot and there's pipes all the way around your house till the water finally comes out at the end. That is a closed system. All the water is staying inside the system. This is also like how your air conditioner works. Your air conditioner has a fluid that cycles between the outside and the inside. It uses pipes to do this. and it uses reducers and expanders the whole time. I mean, that's the whole goal of the air conditioner, is to have the fluid inside the house absorb the energy of the heat. Absorb the heat energy, and then take that heat energy outside the house and vent it outside of the house. That's what makes your house get cold on the inside, by making the outside warmer. But it does so by using a closed system with fluid being moved from the inside to the outside. That fluid is a refrigerant, and it's a liquid, non-compressible in some places, and is a gas, which is compressible in others. So you have liquid inside the house that's absorbing heat and turning into a gas. It's pumped outside, and then it's pushed down by a compressor that forces the heat out of the gas, turns it back into a liquid, and shipped back into the house again. That's how your air conditioning system works. It's how it works on your car. It's how it works on your house. So that uses all of this stuff to figure out what that pressure is going to be and how much pressure you're going to have to add to make that system move the fluid in and out of your house. Now, that's complicated. So let's take a look at how we asked to deal with it. And this is probably the most common kind of question that you could possibly be seeing. And this is what some of your homework looks like too. So imagine we have a table. And on that table is a bucket filled with water. So bucket. Get back to this now and not blow my top a bit. In a problem like this, what they're going to talk about is they're going to say, what happens if you accidentally open a hole here on the side? And you guys all know the answer, right? The hole's big enough, the water's going to shoot out the side. In fact, if I set this problem up right, the water's going to shoot out the side, and it's going to hit the ground. Because this can be both a projectile problem and a fluid dynamics question. Now, the only way we're going to figure out where to put the cup over here to collect the water is if we can figure out how fast the water is leaving the hole. That is a Bernoulli's principle problem. And I want to talk to you about how we solve this problem, okay? This one doesn't look like Bernoulli's principle, but as soon as you see fluid in a cup, it's going to be a Bernoulli's principle question. And there's some weird assumptions we have to make for this problem too. I'm going to talk about the assumptions. But this is not a contained fluid. I'm making that kind of clear here, right? It's not a contained fluid, meaning that it is open to pressure here and here, right? It's not in an enclosed system. But here's how this problem works, and it's not particularly hard. It's kind of fun. And hopefully you'll get the idea of what you have to do pretty quickly. Bernoulli's principle is a principle, it's not a law. But because it is tried and tested, the principle works, because it really is just a statement of conservation of energy. So I'm going to compare the top with the hole. At the top, we've got the pressure at the top on the fluid, plus we have the portion that's about gravitational potential energy, plus we're going to have the kinetic energy. Again, not really energies, but it's the part that's about energy. That's all at the top. We're going to compare that to the pressure at the hole plus rho g and the height of the hole plus 1/2 rho v at the hole squared. Now, in your mind, I want you to imagine this big bucket of water with the hole in the side and the water shooting out the side. Now, if you can imagine it a little bit, there's probably some things that are going to seem kind of silly, but we're going to talk about them anyways. First, both the hole and the top, they're both open to air pressure. You guys see that all right? Because of that, these two will cancel out because they both must be at the same pressure, because the thing's exposed to the atmosphere, so they're both at the same pressure. An enclosed fluid, that's an enclosed system, that wouldn't be true, but the top of this isn't actually applying a force to any surface because it's exposed to atmosphere. Now, this next one is a little bit of, that's the first assumption, is that in a problem like this, both the top and the hole are exposed to the atmosphere, so the pressure is the same at both locations. That's one of the first things we can do. It's one of the first things we can talk about. The second thing, though, a little more complicated, and it requires a little hand waving. So usually there'll be some statement in the problem that will say that the bucket is very big compared to the size of the hole. And that's a weird statement. I mean, why would they want to be telling us that? It's for this reason. They want you to make an assumption based on that statement. Again, you should probably write the statement down. You're looking for it. Remember, it's like there's always some kind of statement like, where they might say, well, assume it's a smooth surface. That's kind of subtext that there's no friction on the surface. Do you guys remember stuff like that? This is a subtext kind of thing too, where they're communicating something that you have to use. And it's like, but it's a weird statement. They're going to say that the bucket is very big compared to the size of the hole. And again, you might be wondering, well, why would they tell me that? Why is that statement important? And here's why, because it's really silly. If they say that the bucket is really big compared to the size of the hole, does the water level descend very fast as the water comes out? I mean, why don't you imagine an entire swimming pool and you poke a hole in the side of it. Would the top of the water of the swimming pool be going down particularly fast? It'd be going down really, really slow. Well, if it's slow enough, you might just be able to say that the velocity of the fluid at the top is basically zero. That's what they're trying to communicate. It's a weird assumption, but it's to knock out that the fluid at the top's not really moving very fast. It's the fluid at the side that's moving really fast. And that's where the rest of the problem comes into play, because you just get rho g y at the top equals rho g y at the hole plus 1/2 rho vh squared. Now, if we decide that the height of the hole is right there, we can make that 0, right? Our reference level for the water. And all we would have to figure out is how high the water is at the top compared to where the hole is. And that would make this term 0, and we'd get the old mgh equals 1/2 mv squared. Right? Doesn't that look a lot like that? I mean, there's no m's, but also the m's would have canceled as they will here, which tells you what the velocity of your fluid's going to be. It's like the marble just rolled down a ramp that was this high. The water comes out of the hole about the same speed as a marble would if it was rolled down a ramp that high. What's that? Square root of 2gh. That's exactly it. So I know it's a lot to talk about Bernoulli's principle just to bring it down to square root of 2gh, but yeah, that's what it amounts to. The fluid comes out of the hole about that fast, and it's because gravity is what's pulling it out of the hole. It's that simple. The air pressure doesn't really play a role because the air pressure is pushing down here, but it's also pushing against the hole there. That's why the pressure cancels out, and we don't worry about the pressure. All we have to worry about is the fact that gravity is pulling the water out of the hole. Once you get that velocity, well, you guys know all about setting up a vertical and horizontal, thing. It's not fun, but then it takes a different turn because suddenly you're worried about the height of the table and where the water's going to strike or where it's going to be in the cup. We'll set this up tomorrow. I've got a nice big tank. I have a hole on the side of it already. We'll take a look and do a quick calculation, see if it works out for us, okay?